That's it. Send me an email. All right. Hello. Good afternoon. Here. You can start the general procedure. Reading, thinking, sometimes maybe calculating, choosing the answer, pressing the button. Whew. So I am going to set up a timer and let you just think it through. Any questions about anything? So you know your answer, 1 for 1, 2 for 2. I'm going to switch quickly just to illustrate again what is happening. That's what's happening. It doesn't matter if it was released from rest or we kicked it. What we know is that it weighs 250 grams, and when traveling through the equilibrium position, the speed is equal to a certain number, I guess 2 or 4, let's see. Okay. 4, so maximum potential energy, that's what we're looking for, U max. Well, first of all, because, well, by now we know the thinking strategy, not usually about what we're looking for, but something more general. The more general word is energy. So we start from thinking about energy, and what do we know? Mechanical energy is equal to kinetic plus potential, and with no friction, it remains constant, which means when potential energy becomes 0, kinetic reaching maximum value. When kinetic energy becomes 0, potential reaching maximum value. That's what's happening. And now we can answer a question about the maximum value of potential energy, because the law of conservation of mechanical energy tells us it just has to be equal to the maximum value of kinetic energy. And to calculate that value, K max, we just need to multiply mass, maximum speed squared, divided by 2. And, well, speed changes with position. But as we know, when position reaching 0, that's what we call the equilibrium, speed reaching maximum. So this number represents, that's maximum speed. 0.25 is 1/4. 2. So nothing new, just to review. Next problem, again about, well, we basically just did it. Yeah. So we just did this reasoning for a different purpose. But again, it's about maximum. Now the keyword is maximum. And what do we know about maximum? Well, there is maximum displacement from equilibrium, maximum speed, maximum kinetic energy, maximum potential energy. So we just said less than a minute ago that maximum kinetic energy is equal to maximum potential energy. This is a specific consequence from law of conservation of mechanical energy. So if you write it like this, now we can solve it for that maximum speed. We know the answer is supposed to be equal to this. The amplitude of position times the angular frequency. We know it's been told, but we don't know why. Now we're just basically proving this fact. That's it. Because if we solve this, 2 and 2 cancels. V max will be equal to square root of k over m times a squared. And this is indeed equal to this. So all other relationships between maximum acceleration and amplitude, maximum force and amplitude, do not require using energy at all. It's just a Newton's law, F equals ma or F equals kx, that's it. But if we want to prove this relationship, that's what we can do, using the law of conservation of mechanical energy. And a better writing. Next problem, same block, same spring, and we've answered all these questions before. So we have calculated everything, U, K, energy. We did this. How did we do that? First, we found the time when x reaching given position, x equals 5 or wherever it is. So, and then from using time, we have found all these variables. Yeah. So, nothing new. Now, using the same strategy, using the law of conservation of mechanical energy, we can eliminate time, take it out of the picture. We don't really need it because, well, first of all, to refresh, to calculate potential energy, we don't need time. We just need the spring constant and position. To calculate the force, well, the x component of the force, we don't need time. To calculate the x component of the acceleration, we don't need time. So only speed and kinetic energy kind of under the question now, under the investigation. Can we find those variables not using time at all? Yes, we can. Because again, the total mechanical energy is constant. It has to be equal to, well, again, K max or U max. But U max, as we know, should be equal to this. So if we moved an object 10 centimeters away from the equilibrium and we released it from rest, 10 centimeters is that maximum displacement, is that amplitude. K, so if we want to calculate now kinetic energy, we can do it using this. Kinetic energy will be equal to total energy minus potential energy. I think I've said it like 6 times now. But on the other hand, the same kinetic energy will be equal to mv squared. That's instantaneous speed. V is a part of kinetic energy. So if we want to, we can solve this expression, which is, again, just a law of conservation of mechanical energy. We can solve it for the speed. K is the common factor divided by m. Then a squared minus x squared and square root. That's speed. Done. And as we know, when x equals 0, which means the object travels through the equilibrium, when x equals 0, speed reaching maximum value, omega times a. When position changes, speed changes, and finally, when x reaching maximum displacement, a squared minus a squared is 0, it instantaneously stops to change the direction of the motion. Any questions? This is what I want to ask everybody now, because this is a copy of a question from a lab, and I want to see what your TFs told you. So what is happening? We take this card, we move it away from the equilibrium, and release it. We know it takes exactly a quarter of a period to travel exactly 1 amplitude. So of course, on its way back to the equilibrium, eventually it travels a half of the amplitude, then another half, then another half, then another half. So the question is, how much time should we wait before it travels the first half of the amplitude? Did you press? What did you press? 3. Is that what your TF told you? Maybe some of the TFs may need to take this class together with you. I'm going to wait for 5 more seconds, so please, right now, just stop thinking, and press anything which comes to mind. 1, 2, 3, 4, 5. Done. Oops. That's exactly what I want. That's exactly what I want. We can solve this problem using different ways of thinking, different approaches. And first, without doing any calculation, we can use a graph. Position, time. position changes. When the position of this card changes, what is the easiest graph? You just came. Are you living already? What is the easiest graph which describes changing position as a function of time? Changing position as a function of time. You could say this, oops, but that's not changing. So that would have been the easiest line, but it doesn't describe the change. So what would be the easiest graph to describe how position changes in time? Cosine is the easiest graph? Parabola is the easiest graph? Line. Exactly. You don't have to even say anything, just show line. So if it starts from, again, if it starts from a certain position away from the equilibrium, the easiest graph would have been a straight line going down to the equilibrium. And that's what we could have called a quarter of a period. And that's what the amplitude. And how do we call a motion like that? That motion has a name. We have several names. That's a week number 1 of this course. So is this a rest? A rest is a motion with no velocity. Yes or no? Does this graph represent a resting object? Does this graph represent an object at rest? No. So we have names. We have a motion with constant velocity, motion with constant acceleration, uniform circular motion, free fall motion, and simple harmonic motion. So which name should we use for this graph? Constant velocity here. So why wait so long? That's motion with constant velocity. There is no acceleration. For the motion with constant velocity, it travels exactly the same distance, exactly the same time. So for the motion with constant velocity, if it travels from here to here, a half of the distance, it should travel from here to here, a half of the time. Any questions on that? But now, the graph for this cord attached to a spring doesn't look like a straight line. The actual graph looks like this. Well, better, but it's a curve. So now, if you look at the graph, you can see when it happens. What is that instant when the cord travels first half of the amplitude? If you look at this graph, that should give you the answer. So these are, again, same answers. Choose yours, please. That's why I always, behind the syllabus, when I ask a question, you wait for too long, to give the answer. If you answered immediately, I could move on. So it's not my fault. Okay, again, let's wait 7 more seconds. 6, 5, 4, 3, 2, 1. Stop. Well, even if I'm not sure if it's a right answer or wrong answer, this answer is much better than the previous because the distribution clearly changed. But of course, oops, come back. Of course, we just have to add one more element to this picture. This is the time, I don't know how we call it, time star time, when the first half of the amplitude been traveled, and you can see it's between these two instances. We also can ask a question, okay, when time is exactly equal to 1/8 of the period, where is the card? Well, in that situation, we have to extend this line. And this will be the position, x hat, the position of the card at t equals 1/8 of the period. No calculations. But of course we can, if you want to do those calculations. It's done right here on this slide. Basically, we just have to ask, okay, if x equals a half of the amplitude, what is t equal to? We have to write the equation. We have to substitute the x with the given position, and we have to solve this equation mathematically. A cancels. Cosine of which angle equal to 1/2? 60 degrees or pi over 3 radians. So this whole combination has to be equal to pi over 3. Cancel pi, solve for time, t over 6. That's an exact answer. Any questions? Okay. I'm glad we cleared it up. All right. This is basically this. So I don't need this anymore. Oh, shoot. This car doesn't have a bumper. All right, you've seen in the lab, some cars actually have a bumper. Like so, when it hits, the bumper compresses, and of course there is a spring. And if we attach the bumper, it's going to be just a card attached to a spring, making a simple harmonic motion. Well, what we're looking for is, let's read. Period of those oscillations. Okay. To calculate the period of the oscillations, we need to know two variables. So we know the mass. And all we need to calculate now is the spring constant. No, actually, the other way around. I better clear it up and rewrite it. Well, this is the cart with this bumper. When it just starts touching the wall. So this spring is free yet, and it's moving at 0.5 meters per second. But eventually it stops. Well, momentarily. Well, usually there's a catcher which catches. It could have been a train car, so, but it doesn't matter. Eventually, the bumper compresses the spring, and its instantaneous final velocity becomes 0. If the spring is free, what does it mean? That means there is no potential energy. Potential energy initially is 0. But when spring is compressed, that means final potential energy is not 0 anymore. What is it equal to? K times that compression squared divided by 2. And if we neglect any friction, mv initial squared divided by 2 plus 0 has to be equal to 0 plus k times delta x squared divided by 2. What we're looking for is k. So k will be equal to m over delta x squared times v squared. And we know m, we know initial speed, we know the compression. Questions, please? It's not about simple harmonic motion per se, but it's about a spring. So as long as we said spring, we start recollecting all the information about springs. And actually, if the bumper would stick to the wall, well, we could observe afterwards simple harmonic motion made by this cord, back and forth, back and forth. For the vertical spring, don't read this slide because it's not for you, it's for me. So I wouldn't forget to say this. This is what you need to know. You see this equation? This equation describes simple harmonic motion for this weight attached to this spring. Of course, we must choose the origin at the equilibrium. But it's a natural condition, we always do that. And now if we look at this equation, there's only one difference between the equation for the vertical spring and the equation for the horizontal spring. It's a letter. Like dozen slides before, 2 lectures before, the same equation had x and x. That was the x component of acceleration, and that was the x position of this object. And now this is the y component of the acceleration, and this is the y position of the object. But it doesn't matter mathematically, it's exactly the same equation. So this solution is exactly the same. There is no difference between horizontal and vertical motion. All you have to do is just replace the letter x with the letter y. That's it. Well, this problem is about a free body diagram. What we have here is an equilibrium. So the force of gravity acting down on this weight should be equal to the spring constant times the elongation of the first spring, spring constant times the elongation of the second spring, spring constant times the elongation of the third spring. But what we want to find out is, okay, we don't have 3 springs, or we don't want to use 3, we want to use only 1. And we want to replace these 3 with only 1, but such that the same weight, when attached, would provide exactly the same elongation. So the question is this: effective spring constant is equal to what? Well, we can write the same equation. So this equation is for this system. This equation is for that system. It has to be equal to the effective spring constant times the same elongation. And now we can solve. Well, mathematically, this is equal to 3 times k times delta x. So this is the same, which means if we take one spring, which is 3 times stiffer, stronger, we can replace those 3 with this one, and it will not change a thing. A pendulum. You know how it looks like. that's what we call a simple pendulum. A simple pendulum when the mass is concentrated in one point, basically. So by now, from the lab, you know the equation for the period. What do we have to do is just, well, now we have to, because it's a circular motion, we have to apply the Newton's law for rotational motion. And tricky part is that now we have to measure angles vertically. But we keep the same agreement. Everything measured counterclockwise is positive. Everything measured clockwise is negative. So if I release this ball, it's speeding up. It's speeding up, and it's moving this way. This way we call clockwise. That's the angular velocity. It's speeding up, which means angular acceleration is supposed to be negative again. But what about the where is it? Where is it? What do I do? So this torque is 0. Negative, negative. The angle is positive. This angle is positive. So that's a problem. So if you want to write how magnitudes are related, well, I is positive. It's easy. It has to be mg times the lever arm. This is the lever arm of the force of gravity, and that has to be equal to, that's theta again, that has to be equal to the length times the sine of this angle, and we have to take magnitude of that equals I times alpha. But if you want to write it using components, sine theta, theta. This component should be negative, but the angle is positive. So to fix that, again, we have to multiply, doesn't matter which side, by -1, make positive side negative or negative side positive. And another thing, a sine is a very complicated function. So only when angles are less than like 5 or 6 degrees, we can solve this equation. In that case, the sine of the angle is practically equal to the angle itself if measured in radians. You can take a calculator and calculate the sine of 0.01 radian. The answer will be 0.01. So we can replace the sine with the angle. We can just drop this symbol. Now this equation is not exact anymore. It's an approximation, but it works very good for small angles. And now we can solve it, of course. It's been done. In the end, we end up with exactly the same equation. Instead of regular linear acceleration, we just use angular. Instead of regular linear displacement, we just use angular displacement. And this coefficient has a very complicated structure in general. We can use it if we want to calculate a period of any pendulum, like this, for example. A rod, attached. We call it a physical pendulum. It still has a period. So what is m? Well, m is the mass of this object. What is I? I is moment of inertia relative to the axis. What is g? 9.8, if it's here on the Earth. What is L? Well, that's the distance from the axis of rotation to the center of mass, because force of gravity is applied to the center of mass. However, for the simple pendulum like this equation becomes very simple. You see, the moment of inertia is equal to mass times length squared, mass cancels, and that's how we get that result. So, first question I'm not going to ask you. Let's say we have two balls, one heavy, one light, but the length is the same. If we look at that equation, it has no mass, so mass shouldn't matter. So they should have the same period. What if we have two identical balls, but one is longer, one is shorter? Which is going to have more period? Well, of course, oops, wrong direction. Here, the relationship. If you're increasing the length, you're decreasing the frequency, increasing period. So longer string, longer period. In fact, this string is 4 times longer than that one, which means this period is twice of that one. Any questions? Look at that link. This is about driven oscillations. A driven oscillation looks like, I crashed it. A driven oscillation looks like this. We need a driver. Well, driver in this situation means the source of the energy, this function generator. And of course, we need to turn it on. It drives this ball, but you don't see much happening. But if I hit a specific frequency, it actually, well, reaching maximum amplitude. And if it wasn't for very strong friction here, it would fall out, you know. That's what we call resonance. Resonance happens when the external force acting on the system has exactly the same frequency as the natural frequency of this system. So you see, 1.05, so about 1 second. So when we drive with exactly the same frequency, in that case, we pump energy in the phase with this motion, and, well, eventually, if there is no friction, it breaks. We don't want that. That's why, for example, if you watch troops marching across a bridge, they don't march, you know, left, right. No, because if by any coincidence the frequency of stumping will be equal to the natural frequency of the bridge, and every bridge is moving. Look at this link. It might break. We are done with simple harmonic motion. We start a new topic which has a name, fluids. It's about water, milk, beer, and anything else. Please, that's your last question for today. Answer this question to me. The experiment is this. Well, that's later. Okay. I really need more space. Oops. As long as I'm ready with this, I'm going to stop collecting your answers. So. I'm just giving you more time. This is not the actual Diet Coke. Yeah. Well, so that's what's exactly happening. That's a historical moment. It has to be taped. It has to be captured. What's wrong? Oh, I see. What's wrong now? Okay, nothing. So you're witnessing a historical moment. Well, Archimedes actually did it first 2,000 years ago, but basically. Any change? That's all. So now let's see if all righty. I'm going to keep this. That is a historic moment for me, for you, for the mankind. So all we have to do is just draw a free body diagram. If you have no water, of course you have only force of tension and force of gravity. But water is a medium. When we put it into water, did you see what was happening to water? The level rises. Why? Because the ball pushes on water. What does water do? It's pushing back. The third Newton's law says if the ball is acting on water, the water is acting on the ball. And that is the third force which must be a part of this free body diagram. So none of those pictures had three forces. The correct answer is neither. The correct free body diagram must clearly show three forces. And now, what about this force? When the ball is in the air, gravity is equal to the tension. When the ball is in water, the new tension now is in the reading. It takes too much too long. How can we find out the property of that force? Well, we have to repeat the same experiment Archimedes did a long time ago. I need more water. So we need to fill it up to the brim, like this. So now, all water displaced by this ball, what will be happening to it? It will be collected in this pen. So this is the first reading. And this is the second reading. And the difference between these two readings is equal to the force acting from this water on this ball. But what can we do now? Now we can take that water displaced by the ball. We can put it on a scale. And we can read it. Oops. More or less. It's, you're going to do the lab, so you're going to have exact numbers. But this is the principle, the strategy. So this is the number which tells us the weight of this water displayed by this ball. On the other hand, we know that the force acting on this ball has to be equal to the reading number 1 minus reading number 2. Well, reading number 2 minus reading number 1, right? Turns out these numbers, oops, where is it? Where is it? Here. Turns out these numbers are equal. The number which we get for the force acting from the water on the ball is exactly equal to the weight of the water displaced by that ball. This is just a fact. An experiment proves it again and again and again. Well, first of all, if it's a new force, we have to give it a name. And that's the name. We call it the buoyant force. A force acting from a medium on an object called a buoyant force. Name. First. Second, how do we calculate it? Well, this is how. The buoyant force is equal to the weight of that water it displaces. Now, this ball is heavy, it sinks. I can make a ball which is exactly big as this one. Is it going to sink? Of course not. It floats. So what's the difference between this and this? Density. We have more stuff in it, so it's denser. So naturally, we need to introduce a new physical quantity, which we want to use to relate that property, how much stuff is inside. We call it the density. The official definition of density is the mass over 1 cubic meter of that material. So if the volume is equal to 1, this number is equal to m. Of course, all densities have been measured. This is your homework assignment. Density of water, if we use international system of units, is kilograms per meter cubed, 1,000. So if you have a cubic meter of water is like this. A large cube of water. So it weighs 1 ton, 1,000 kilograms. But we don't use very often kilograms when we talk about this particular topic. We use grams, centimeters cubed. So which of these numbers, that's your homework. I will ask this question on Monday. And now, how do we calculate weight? Weight equals mass times gravity. So the weight of the water displaced has to be equal to the mass of that water displaced times g. How do we calculate mass? Now we know we can relate it to the density and the volume. So this is the final expression for the buoyant force acting on any object, Like this, for example. There is a buoyant force acting on this balloon. That's not water which makes it, yeah? the air. So gravity pulls down, string pulls down, buoyant force points up. That's it. All right, I'll see you on Monday. You have a question? About what? Second. Well, I just saw this problem. I think that's even easier because if you apply the same force, each spring adds the same amount of length, right? So you should have two pictures. Like in my example, I had a picture of three springs, and then I had a picture of one spring. You should have because one picture represents two springs connected in series, and then another picture should represent only one spring. That spring which you can use to replace these two. So do you have that second picture? Oh, that's a problem. So if you, this is what you have. This is your, let's say, this is a single spring. And if you attach a weight to it, like that, the free spring. If you attach a weight to it, it stretches like this. That's a new equilibrium. That's a stretch. And this stretch equals less mg, that's k times delta x. So k times delta x equals mg. Now, if you take two springs like that, first and then second, and you attach them, each will be stretched by the delta x. So you got delta x here, and the second one got another delta x. You have mg now, but the total elongation is twice. Now mg times k effective times 2 delta x is the new equilibrium. So k effective will be equal to mg over 2 delta x, but mg over delta x is just that original k.
Yeah.
So it's k over 2.
Yeah.
Okay, we're done. With everything.
So that just put that on card?
It doesn't matter, I just take everything.
Does that need to get poured out or anything?
You know what? I don't need this one, but I want to keep that one. So I want to keep the color. You better take this by hands and bring it by the same time. This can go on a car. I think that's it.
That need to come down?
It will. Yeah.
How long?
Anyway, I don't know. We'll see. That's an experiment. I'll check on Monday. Where's Rahul? Have you seen Rahul?
Yeah, he's in there. Just, finishing up some work or something.
No. As long as you fine with that, I don't care.
I know 5 p.m. on Fridays is always a busy time for physics students.
It's a homework due too?
Yeah.